Hey, good evening, everyone. I hope those who will be going through this recording, since nobody is there attending online today, I hope that most of the people have their doubts cleared. So, I'll record this and share it on YouTube. You can go through the link and check out this recording. So, I'll just share the screen. So in this week, which is the module 5, we have discussed uh, MATLAB programming for nonlinear algebraic equations. Like we saw how we can solve the nonlinear algebraic equation. Previous week, we had gone through linear algebraic equations. So this week, uh, in an advancement to what was taught in the last week, so we are going to see nonlinear algebraic equations. I hope you have all watched the lectures in module 5. So in the first module, we discussed about this nonlinear equation in a single variable. So a simple example was here in which uh, this was the nonlinear equation which we had to solve. 2 minus x plus log of x. So ln is nothing but log to the base c is equals to 0. So since you can see that this is a nonlinear equation, and sometimes, like not sometimes, but a lot of the times, solving a nonlinear equation is difficult. Like you can't directly analytically solve them uh, every time. So you have to rely on some kind of numerical methods. So we'll see what different kinds of numerical methods are there to solve these nonlinear equations. So as you can see, this is the plot of this uh, nonlinear function. So as you can see, it is intersecting on the x-axis two times. So it has two solutions. So one is 0.1586 and the other is 3.1462. So when we have a linear equation, we basically will have only one solution. But for nonlinear equations, we can have multiple solutions. In linear equations, we have seen that it can have a zero solution, or it can have a unique solution, or it can have infinite solution. But it won't have like two, three, or four number of solutions. So it might have infinite solutions, or it might have unique solutions, or it might have zero solution. Here we can have uh, like multiple solutions. Like here, basically, we have two solutions. Depending upon the equation, like we have a different equation. Might have three solutions, of course. So we need to uh, find out these solutions numerically. That's what uh, the uh, objective of this module is. Like, how can we find them numerically? So the solution is the location where the curve intersects the x-axis, as we are seeing here, 2 points, but if it is intersecting the x-axis. So, like as professor has said, professor has said in the lecture that you can also, like if you want to go deeply into this, a little bit deeper into these methods which we are going to use in MATLAB for getting the solution to nonlinear equations. you can get like detailed derivations of methods and like a lot of uh, more insights into what these methods have and uh, what are the advantages of each and each over the other different kinds of things. If you want to learn, you can go through this computational techniques course taught by Professor Nitin Kaisar itself. So, so it has all these uh, lectures on various methods which we are which we have seen in this module. So in a more detailed and uh, nuanced way. So so this is a general uh, uh, like equation. Like this is an example for model of area, which this is the equation. So uh, and we want to find out this C of A. I think I assume that this is concentration. So you want to find out because this is a nonlinear. You can see that there is this is like uh, 1 by C A square. So obviously this is a nonlinear. So so we want to find out what is this uh, CA when f of CA becomes 0. So general strategy would be so when we do nonlinear, solve the nonlinear system of equations using numerical method. So what we do is we basically start with an initial. So it can be any random guess, but the problem is like uh, these methods are like very sensitive to these initial guesses. So depending upon the problem and the domain knowledge, like if you're working in mechanical engineering or if you are um, a civil engineer or if you are a mechanical engineer, depending upon the problem you have, you might have a feel that your solution lies near to some value. So depending upon that, we take the initial guesses. So so it's like randomly choosing initial guesses might lead to divergence, and you might not get the required solution, and the method may fail. So that's what like we have to be very careful uh, while choosing these initial guesses. So we have a like we take an initial guess and uh, we check the value of f of x at that initial guess. And if this difference is like, let's say if this difference, like if basically solutions like f of x has to be zero. If you have taken this as your initial guess and you are getting some value of f of x, and if this f of x is very large, it means that you are not like uh, you are not like close to the solution. So you have to move either left or right. So then you have to move, like you have to update your guess and check again, and then like we go on doing this until we have a stopping criteria. So I might say that f of x should be very less, or you can say that uh, like as you go on doing the iterations, f of x I plus 1 minus f of I uh, should be less than like a very small number. So basically like uh, or you can say that sorry f of sorry xi plus 1 minus xi should be less than like very small value. So your solution like should be going like closer and closer and closer. Then your as you go near to the solution, so your xi values also uh, with iteration should go like near to the solution, and there should not be like much difference between previous iteration and the uh, present iteration. So like different kinds of stopping criteria you can specify. Based on that, you can like take that current value as the solution of your quantity. So first is the bisection method. So in this, we start with two initial guesses, XL and XC. So Basically, we want to take initial guesses such that the values of uh, f of xn and f of xu are different. Sorry, signs of f of xn and f of xu are different. So you can see that here, here, if I take a value here and if I take a value here, uh, let's say this is f of xn and let's say this is f of xu. So f of value of f of xu will be negative. F of x value of f of xn would be positive. So in bisection methods, we should take the initial guesses such that these values of function, signs of function, uh, are like signs of functions at x and x are opposite. So which means that basically uh, we know that between two values, like if the function is like changing its sign, it means that somewhere in the middle of this or somewhere in this interval, the function is intersecting the x-axis, and that's why we might have the solution in this interval. So that makes our guess like a very useful one, and it will be like uh, easy to go towards the true solution. So then we will make a new guess out of this uh, these two initial guesses. That is like we take the midpoint of these two, and again we'll calculate f of x. Uh, and we will again see the signs of f of x nu, f of xl, and f of xu. So we take f of x nu. So now we will take another initial guess in which we replace xl or xu based on the signs of f of xl and f of xu with respect to this f of x. So let's say if f of x nu and f of xl have opposite signs, then we will take xl and x nu as my new guess. Or if they both have the same sign and x nu and f of xu and f of x nu have opposite signs, then I take x nu and x nu as my uh, new guesses. So that's how we do this. Uh, we take like uh, again we take a uh, new guess x nu, and we go on doing the iterations till we have, let's say, till we like we get our solution. Like we can say that f of x is like f of x is very small, or f of or you can say that interval uh, or interval like xl minus x is like very small. So whatever the stopping criteria we specify, so till that we go and then we get the solution. So basically, like this uh, dissection method and uh, regular Fibonacci. These methods are called bracketing methods. So because we take two initial guesses, that's why like and and such that these have opposite signs. That's why these called like bracketing methods, and we can get the solutions. Let's see an example. So we have already coded this whatever. This is the same thing which was discussed in the class. I'm doing it again. And so this is like 2 minus x plus log x is equal to 0. So we are going to solve it using the bisection. So so we are taking this two initial guesses. So one is the xl is equals to 1 and uh, xu is equals to 4. Okay. So here because I can plot this let's say uh, I'll do one. I'll just x is equals to which is 0.1 to 600 and let's say y is equals to what what does we have 2 minus x plus log x. Anjali, can you hear me?
Yes, sir, I can hear you.
Okay. Okay, so nobody joined, so already started the recording, but I'll just revise whatever we were we have gone through this module 5 in this week. So basically, last week we have seen in module 4 various methods, numerical methods to determine the solution for linear system of equations. So in this week, we are going a step further and we are going to see how can we solve nonlinear equations. So first we are going to see uh, nonlinear equations in single variable. So solving nonlinear equations is basically a bit of a complicated task because you might not get an analytical solution. When I say analytical solution, let's uh, like closed form solution. You cannot get it always. So we have to uh, mostly go through these kind of numerical methods. Let's say you have something like equation if I give you an example, uh, you have some equation like x square minus 2 is equals to 0. So solving this is a very easy task. It is a nonlinear equation because let's say here in this in this f of x is x squared minus 2. So if I want to find out the solution of this nonlinear equation, which is f of x is equal to x square minus 2, I just have to put f of x is equal to 0, which is x square minus 2 is equal to 0. So I know that uh, this is a very simple problem. Uh, I can take x square is equals to 2, and I know x will be plus or minus root. So I can get an analytical. But let's say if you have something like instead of this, you have something like uh, uh, f of x is equals to some e power x plus sin x um, minus. Can we uh, find out the solution of this? Like if I equate it to 0, can we analytically doing this kind of sending like adding plus 2 on both sides and taking the uh, of square root on both sides, I get x equals to plus or minus. But this non-linear equation is quite complicated. I cannot simply give an analytical solution to this nonlinear equation. So that's why we go to numerical methods. So numerical methods will not give us like accurate solution, but we can go very near to the true solution. So that's what objective of this module is. Like we are going to see some numerical methods, different numerical methods, which we can use to solve nonlinear equation. So this was the example given, like 2 minus ln x plus ln x uh, is the nonlinear equation, and these are the two true solutions of this. So this we know because like we can just plot and we can see where it is intersecting at the x-axis. So nonlinear solutions, nonlinear equations can have multiple solutions. In this case, we have two solutions. Like uh, as a like we also saw in this case, right? X square minus two is equals to 2. Here we know that we have plus two or sorry plus root two and minus root two. We have two uh, solutions. This is also a nonlinear equation. So similarly, here also we have two solutions, but this can like depending upon the equations, like you can have even like more number of like you can also have a single solution. You can also have a two number of solutions. You can have three, four, multiple solutions can be possible. But in linear equations, like when I say linear equations, basically it is a straight line. So straight line can like basically have like it can intersect x-axis only at uh, one point. Like it cannot go like a straight line cannot go and bend like this and like on it. So linear equations have only one solution. Or let's say if your straight line is like parallel to x-axis, it intersects like parallel and it coincides with the x-axis, then you can say that my equation have has infinite number of solutions. Like if it coincides with the x-axis, or if it is like it is parallel to x-axis and lying somewhere else, then I can say it doesn't have a solution like that. So it can have a single solution, it can have an infinite solution, or it can have no solution. So nonlinear equations can have single to multiple solutions, and they can also have no solution. So that's the uh, difference which we can see in linear equations and nonlinear equations. So this is just a example of a model for a reactor. Like if you are from chemical engineering or someone who knows chemistry, might relate to it. But like but we are not like tied to like this example. Like there can be many other examples in your field which you can relate to. Like nonlinear equations come in every other field where you models things. So so generally what we do is like whenever we go for a, numerical solution, like in whenever we resort to use some numerical methods, basically we have to start with some initial guess. So using this, uh, uh, like taking the initial guess is a very important thing because sometimes, like if you are not like like most of the times, like if your initial guess is like very bad, you will not get the solution, and and you're like basically here we are going to going to do our method in number of iterations. Like as you increase the number of iterations, your solution will diverge a lot. So that's why whenever you solve a nonlinear equation, so you should have the initial guess which is like very good, so that you can get a solution in less number of iterations and like with less computational complexity. So I like you cannot like like mostly if you are taking a random guess for your initial solution, you might not get ending up the solution. Like it depends on your luck. But if you are someone like who have a good domain knowledge, like if you are some like let's say if you are some mechanical engineer or if you are a chemical engineer, uh, you have a feel that my solution will lie between these points, like it will lie in this interval. You will have a good feel. So depending upon that, you try to take the initial guess. So we don't take an initial guess which is very random. So depending upon the domain knowledge which we have, so we take an initial guess. Okay. So give me just one. So then we take an initial guess, uh, and we'll check the value of f of x at our initial guess. Let's say you take f of x is equal to 0. No, no, we'll not take f of x is equal to 0 because here it like ln x, because basically ln x goes to infinity at this point. So we don't, like let's say you are taking some value like initial guess is like f of x, x is equals to 1. So you substitute x is equals to 1 and you will see what is the value of f of x at this point. And you see that you will get some value like f of x will give you some value. If your f of x is like very large and it is not equal to 0, it means that your initial guess is wrong. Then what you have to do, you have to go to the next iteration and you have to modify your guess. And you go, so like depending upon the method, you go to a new guess and you check the value, like you take the new guess and you check the value of f of x again, and you will see again the value of f of x. This is like, if this is like reducing, it is a good news. Like if it is again increasing, like maybe not a good news, like a lot of the times. If it is reducing and if it is like very near to 0, then means that means like you have come very near to the solution. And if f of x is like uh, perfectly 0, then it means that your guess is true and you have uh, come to the solution. So your guess is the solution which you will get. You have got from your analysis. So basically, like we'll keep on updating our guesses, and we'll have some kind of stopping criteria. As I have said, this might be my stopping criteria, like f of x. Like I can say that the value of f of x should be less than some delta. So delta is like a very small value, like 10 to the power of minus 5 or 10 to the power of minus 6, you can say. So if my f of x goes below that, I'll say, okay, stop, and I can take the whatever the value of uh, x which I have, like the guess updated guess which I have, I'll take it as the solution, and I'll I have solved the problem in a numerical way. So you can see that I have said that my f of x is like, I'm not telling that f of x should be equal to 0. My stopping criteria is f of x should be less than delta, which is like a very small value. Basically, it means that I am satisfied with the approximate solution. That is like a very reasonable solution. I might not need to go iterating till I get f of x equals to 0, because it will take me a lot of computational effort. Like I need to run my computer uh, a lot more, like a lot more number of iterations, like wastage of resources. So I can compromise a bit and I can take whatever the solution, like based upon the staff criteria, and I'll get a good solution. So then, like the first method which we have is the bisection method. So in that we have a single variable uh, only, like we are basically taking the whatever the example which you have taken. This is also a single variable which is x. So if I want to solve this nonlinear equation 2 minus x plus ln x. So with the bisection method, basically I have to do start with two initial guesses in this method. So the initial guesses which I take xl and xu should have for these initial guesses the value of f should be uh, having opposite signs. So here, let's say for example, I can take uh, this and this, this and this as my initial guess, because you can see that here the value of f of x is positive and here the value of f of x is negative. It means that basically it means that I can like whenever between 2 points the value of function is changing from positive to negative. Intuition says that it might be crossing the x-axis at some point in between these 2 points. So I know that if I uh, keep on taking my guess between these two initial conditions, I will go near to this solution where f of x is crossing the x-axis and f of x is 0. So that's why in bisection methods we take this kind of approach where we take initial guesses which in which f of x has opposite signs. So then after that, after taking the initial guesses, I'll generate a new guess such that it is the midpoint of these two. I'll take xl plus xu by 2, and again I'll do the same exercise. So I'll take f of x new, the sign of f of x new, the sign of f of xl, and the sign of f of xu. If f of x new and f of xu have opposite signs, then I'll take x new and xu my as my new guesses. And if x new and xl have opposite signs, then I'll take these two as my new guesses. So whatever depending upon the signs of x new xl, f of x new, f of xl, and f of xu, I'll take in my updated guess I'll take only one of these xl or xu, and again I'll take a new guess which is let's say f of x new plus sorry x new plus xl by 2. I'll keep on doing it till my stopping criteria is satisfied. So we have this let's say I'm here just plotting this uh, function which we have got. So 2 minus x, just a random, like I'm taking few points and I'm plotting this. Let's see how it will turn up. So this is my plot which I have plotted. Like I have basically I have taken from 0 point. Let's say I'll take it like 0.16. Okay. So plot it, taking some time to plot because I have taken thousand number of points. So it's taking this. Okay. So this is my plot, and uh, I'll also take z is equal to 0. can just add this. This is the can in MATLAB I can also edit my plots like this on uh, here. You can see we have a lot of options. I can basically I want to add a line. Very bad. Yeah. So this is my x-axis, which is x is equals to 0. And I can see that it is intersecting at 2 points. So here, so basically I know that uh, based on the plot, like because we don't have the domain knowledge, whatever we have, like to take the initial guess based on this plot, I can say I can take 1 and 4 as my initial guesses. 1, as you can see, at point at 1. So this function has a positive value, and at 4, this has a negative value. So I'm taking this as my initial guess, and I'm again like uh, I have to check it like so. Whatever the initial guess which we are taking, is it yielding opposite signs of f? So we'll check it. So if basically if I do the multiplication of FL and F, I should not be getting greater than 0. So if they have both positive signs or if they have both negative signs, I can say that uh, the multiplication of it will give me a positive value. So that's why this should not be greater than 0. So if it comes greater than 0, I'm saying that I'm telling MATLAB to throw an error that initial guesses should have different signs, and I'll modify it. So if this condition is not satisfied, then I can go to the next step. So again, like as I've said, like I have to do a lot of iterations. So firstly, like XL and XU, I'll have an error. So then after that, I'll generate a new guess, which is X new, which is the midpoint. And then after that, I'll evaluate F new. And I have said, like I'll check the values, signs of FL, F new. So if FL and F new have the product greater than 0, it means that uh, uh, this uh, is not like we have to we can remove Excel. So instead of Excel, I'll take X new, and instead of FL, I'll take F. So and like the other guess will remain same, which is X new. So else I can say that uh, I can keep FL. I can keep FL and I'll change X U and X U. So like that, I'll keep on doing a lot of iterations. Like here, I have not kept a stopping criteria. So like mm, basically, I'm saying MATLAB to run 50 iterations. So I'll keep on doing it. Like let's say if I run it, so the approximate route which comes in between this 1 and 4, uh, because we have taken this initial guess. I have taken this initial guess as 1 and 2. So I'll get this route only here. So I cannot expect my method to give this route. So which occurs between basically 0 and 1. So I can get the route between this 1 and 4. So which is 3.1462. It's a very good guess to my solution, and like the error is also like order in order of 10 to the power of minus. So I'm very happy with it. So let's say if you want to find out the other solution also, like then you can say you can take this as some 0. I don't know, 0.001, and this as one, let's say. If I do it, so I'm getting this approximate root as 0.158. So this is also very good guess, and the error is also very small. So that's how we can uh, use the bisection method to find out the roots. So for nonlinear equation, a very simple method, but the thing is like MATLAB itself has a function, inbuilt function, which is f of 0. So I don't think it is like this bisection method, but it is an inbuilt function. It is a very efficient uh, function. Like whatever the bisection method which we have coded might not be a very efficient thing. So this function, if we use it directly, it will give a much more efficient computational efficiency. Whenever I say computational efficiency, like it will require internally, it will take less number of calculations, and like chances of uh, getting an efficient solution is very high. So that's why like this is an inbuilt function f0. So I can use it. Like the syntax of it is like this. So basically, we have to define a function first. So whatever the function uh, which you have, like you have to define it, and then you import, then you call that function in this f of 0, and you also have this initial guess. So these are like this is the vector of initial guesses. Basically, you should have two guesses, xl and x, uh, for each variable. Here, because the only x is the variable, so for each variable we should have two initial guesses for f of 0. So this is like the same thing which we have. This is the function for bisect, and let's say if I remove this and f0 x, if I take x 1 for bisect, and I'll take, as I've said, my initial guess, x naught is equals to 1 comma 4, 1 semicolon 4. Okay. Okay. So I'll run it. There is some error. There is some error. So you cannot continue because using the this file name is rename it to totem file. So now it will work. As always, I have said it would be very good to add these two commands in your script file if you don't want your program to be affected by the previous values which are already saved here. So as you can see that this f of z is giving a solution by 3.146. So that's like if you have a bracketing, like if you want to do this bracketing, uh, use this bracketing methods, like where you take two initial guesses for your variable for which you you want to find out the solution. So then you can use F0, efficient function, which is an inbuilt function in MATLAB also. So to do your uh, analysis. So we can also like uh, have the other methods like regular false is also a bracketing method, but we are not going to particularly see what this regular false is. If you want to learn more about the regular false method, you can go to the uh, computational techniques course and learn more about it. Let's see some example where we can use bisection method. I think so. I'll take this function. Let's say what is this function? So I'll replace it here. So my function is 1 by x minus 10 plus 0.87 into ln log 6 plus 25 by. So this is the function which is given here in the practice assignment. I'll just, let's say I'll just plot this for just equals to lim space 0 to 1, 1,000 points, 100 points, by y equals to what is this? 1 per bisect of x. I will just call this one. Since I don't know the initial guess for this, I'll just plot and see what can be my initial. I'll run this 4 lines. Let's see. Evaluate section. There is some other. Okay. I'll just have to basically run a loop here instead of that. I'll just copy. Just copy this. Paste here. And I'll plot it. I have to do this element wise operation. Now I Okay. So this is my plot here. For this function, I can see that there is one solution, which is only one solution to this in this interval. It lies somewhere here. I'll just shorten this interval because it's very long one. And I'll plot it. So now you can see that your solution is our solution lies between, let's say, I can say it lies between 1 and 0. So I can take these two as 1 and 0 as my initial guesses. 0 and 1. Let's say what this will give. I'll run this whole code which we have written and run this whole script. Function values. Okay. 0 if I take, it goes to infinity. Well, and so anything by 0 is infinity. So I'll just take a small value. Okay. If I log this, I run this whole system. So I'm getting this value 0.1768. So it's like very near to this. Where lies my solution? So so f of 0 is giving like a good approximation to my function. Let's say if I want to use a bisection method. So we have this code. So a bisection method instead of like, so we are calling the bisection like one for bisect in which the function is like written. So uh, we'll take initial guesses like which is 0.001 and 1 and we'll do a so uh, we'll do like the analysis using the bisection method and try to find out the solution. You can see well, all the steps are given, and also I have a specified the tolerance criteria here. So if my error goes below some value, I'll stop and I'll tell MATLAB to break out of the loop and give me the solution. That's what. So I'll run this. Let's see how it will be. So I'll always like add these two lines. And I don't want my other uh, modes to influence or methods to influence. And I'll run it. So you can see that bisection method is also giving this uh, solution, which is 0.161768 near to the solution, like as we can see from the plot itself. And also the error is like below the tolerance, and it is taking, I think, it is taking 21 number of iterations to go to the solution. So different like uh, non-linear equations can be solved like this using the F0 command, or also you can also use uh, dissection method by hard coding yourself instead of using the F0 command. You can code your like you can write the code for bisection method and you can use it like this. So that's how that's what bisection method was. So I think it's clear. If you have any doubts, please ask me in the bisection method. So Next, we have the fixed point iteration method. So this is also a numerical method, also known as the method of successive substitution. So here, uh, whatever the nonlinear equation which we have, we make that nonlinear equation in this form, which is x is equals to g of x. So whatever the f of x you have, basically you you will add plus x. Uh, f of if you let's say if you have f of x is equals to 0, then you can basically add f of x uh, uh, like uh, on the both side of the equation you can add plus x. Then it will give uh, this kind of equation which is x is equals to g of x. So and after that, like you will have basically like we'll have a initial guess. Like here we don't need two initial guesses. We are happy with a single initial guess. So a single initial guess will be taken and you will evaluate the new guess, which is f of sorry x of I plus 1 will be equal to g of x of I. So you will keep on iterating it uh, until you have some until you go towards the solution until you go uh, uh, and satisfy your stopping criteria. So like which is xi plus 1 minus xi is like very small. Then like you can say like MATLAB to stop the iterations and give you the solution. So we'll see what how we have seen like this. Where is the code? Yeah, fixed point iteration. And just change this name. It's basically used in TXT format. I have to change to dot. So here you can see that uh, we are basically giving like uh, we can make this 2 minus x plus log x into this form of x is equal to g of x, uh, which can be g of x is equal in which like x is equals to 2 plus ln x can be a one kind of uh, form which you can take, and also x is equals to e power x minus 2. Both of these can be possible. So we have seen like uh, doing this like with both the cases, but like one will be giving good solutions and like other will be divergent. So like we have an initial guess, only a single initial guess we need. We don't need two initial guesses as we saw in the bisection. Right? So we also have a stopping criteria, and we also uh, specify maximum number of iterations. Like if your solution is diverging, and it is not going towards tolerance, it is not going below the tolerance. It's like if you don't have maximum iteration specified, it means like it will go on iterating infinitely. So what's the point of doing uh, infinite iterations if your solution is not convergent? So we have some criteria that in these many iterations, we'll see. Like if our solution is like not going to not going like if your tolerance is like if your error is not like increasing by with number of iterations, uh, then okay. If your solution is not convergent, then you can increase the value of maximum number of iterations to 100. Maybe it will converge. But if your error is increasing with uh, increasing number of iterations, it is not a suitable guess. Then you can have to go. Then you have to go and check your initial guess and uh, again perform the methods, iterations, all these things we have to do. So let's see. First, we'll take this 2 plus elements instead of this elements. And we have the error. So error is x minus x1. So with increasing number of iterations, so uh, the latest guess and the previous guess, uh, the difference between these two guesses should be going like uh, should be decreasing, decreasing, decreasing. Like, and it should be less than some tolerance value. So that's what the error which here we are taking. So we are taking the absolute value. Okay. And after doing it, like uh, uh, we get a new guess, we find out the error, and then we take this new guess as the old guess, and we'll find out another new guess. So we'll be doing on, doing on, doing on, and we'll also check if this error is less than tolerance. If it is less than tolerance, we will break out of the loop and we'll get the solution. Let's see how it will react. So we know that uh, it's like we have the solutions already, like 3.14 and 0.5, sorry, 1.5 something, right? So two solutions are possible for this. Let's say if I run this, I'll also add clear all and CLC here. If I run this, there is some kind of, sorry, this lnx is wrong. So this is basically log x. So log to the basic is in MATLAB, like you can directly write log x. If your log has a base 10, then you have to write log. So I run it. Let's see what. So here I am getting 7, and the value of x which I am getting is mm, it's 3.1462. So after this uh, number of iterations, so uh, 7 number of iterations, I am getting the true solution. So regular Farsi method is giving me a solution. So let's say if I take initial guess as let's say 0.001. So 0.001. Say if we can get the other solution which we have. I run it and see, yeah. So I'm not getting it. So I'm also getting a imaginary part in our solution. So because of this log thing which we know. So that's why we are getting it. So like because log of negative numbers, so it's not like good the thing. So that's why let's say if I take only like instead of 0.001, we'll take x naught is equals to 1. My initial guess is 1. And I'm also here also I'm getting 3. Let's say if I take 0.5. Here also I'm getting. So advantages and disadvantages. So I'm getting this thing. So let's say if I take instead of this 2 plus ln x, if I take e power of x minus 2, so what does it do? If I take this and if I run, so now you can see that I'm getting this solution 0.15. So if I take, let's say, this, uh, I'm getting 0.1. Let's say if I take this as 2, initial guess, I'm getting 0.15. If I take 3, here also I'm getting this. If I take 4, if I take 4, this is not basically, this is diverse. So, like, basically you have to choose what you have, like, the function like g of x, you have to choose accordingly in your. So this is more stable one. So it is giving a solution like whatever we put, like 2 plus 3 plus. So if I'm going beyond this range, what was that? Let's say what is 2 minus x plus x. not this function. 0.1. 0.00. It's not this 6 earlier. So this is my function, right? So here you can see, let's say I'll plot it till 4 only, right? It's not good. Okay. So here, like if I go beyond this solution, which is 3.14, whatever, 146, if I go beyond this solution, uh, if I am taking my functional form of g of x as this, it is not giving and it is basically diverging. So if I take this, it will not diverge. It's 2 plus, okay? So if I run this, so now you can see that even if I'm going beyond 3.14 or something, if my initial guess goes beyond this also, I'm getting this solution. So basically a lot of trial and error goes in numerical methods to choose the initial guess. As I've said, like if you have domain knowledge, whenever I said, like you have your equation, right? So you might have a good feel that this is my solution. And also, depending upon the equations which you have to solve, like there might be a lot of literature around that. Whenever I say literature, like in like if there are like some established equations which we have to solve, like the reactor equation which we saw, or like some like if you have some like a deflection for a beam or something like that, like, which is very established in textbooks. So they will all like depending upon the equations, like they will tell you to use this method to solve a nonlinear thing or something. Like based upon that, like we can choose our method and also we can choose our initial guess and we can get a solution of our nonlinear equations. Lot of trial and error. Sometimes you might get, sometimes your solution will be diverging. Again, you have to look into your initial guess. And again, you have to look into your method. Like, if this is the best method to solve the nonlinear equation which you have. If I can I use the secant method? Can I use the dissection method, or can I use fixed point iteration? So, depending upon lot of factors, so we have to see what we can use. So, this is the fixed point iteration method, like method of successive substitutions. So, as we have seen, like we have to take our guess like this. So, uh, so we have to take this kind of we have to convert our equation f of x equals to 0 in this form x equals to x, and we'll get a new guess by taking a initial value, and we'll do the iterations. And if we see our error is reducing, and if it goes beyond, it goes below the tolerance criteria, which you know, then our uh, criteria is satisfied, and we can get an approximate solution for the nonlinear equation which we are solving. The other method, which is like very famous to know, solve the nonlinear algebraic equations, is the Newton-Raphson method. So Newton-Raphson method, basically this is you can uh, like uh, you can basically derive it, like it is a very simple thing. Like if you go to this computational techniques course in the module for part two, Professor Niket Kaisara has clearly explained how you get this. Basically, you take a initial guess and you, at that point, like let's say this is your curve, right? Uh, uh, where is that? Yeah. So you take an initial guess. At this point, you find out the derivative. Okay. And and you see where it is crossing the x-axis, and based upon that, you will take again a new guess, and again uh, you'll take the derivative here, and again uh, you see where this tangent is crossing the x-axis, and with this you'll go on doing it, and you'll get a solution. So that's what like in Newton-Raphson. So if you want a more detailed explanation, you can go to the lecture here. So this is the formula, like which is uh, xi plus 1 is equals to xi minus f of xi by f dash of xi. So basically this, if you send this xi to the left side, which xi plus 1 minus xi is basically delta x. So uh, delta x into f of x, it is basically like y is equals to uh, m into x2 minus x1. So this is what we are doing. We are taking the tangent, and we are trying to see where it is intersecting. So that's what the Newton-Raphson method does. So you have this, like we can solve this same problem. So like Newton-Raphson method, basically this this quadratic rate of convergence is basically like it will like as you keep on like iterating. So the error which you get is uh, like has a quadratic relation with respect to the previous error. So it fixed point iteration, uh, on the other hand, has a linear rate of convergence. So basically, quadratic rate convergence is faster. So we can say that Newton-Raphson method is efficient when compared with respect to the fixed point iteration, because it will give us solution faster than the fixed point iteration. So that's why this is like a widely used method. So Newton-Raphson method is a widely used method. Like wherever you see, like in lot of at least in my field, like we use it a lot, like in mechanical engineering or civil engineering. So Newton-Raphson method is the method which we use if we want to solve some nonlinear equations or nonlinear system of equations. So what let's see how it is. Like we have coded this. This is the same code of the class. I'm adding it. So the same thing which we are here solving, we are solving here 2 minus x plus x. So we have the initial guess as x equal to 2. So this is our function, and this is the derivative of our function, and this is our new guess, which is x minus f by d of x. So we have we basically we have some initial guess, like we take it, and we get the new guess updated it. We'll update it, and after that we'll see we'll see if the error is like reducing, if the error is small, and convergence criteria is checked. If the convergence criteria is checked, and if it is satisfying, we'll break out of the loop, and we'll tell that this is the approximate solution. If this is not satisfying, we again go and do the other iterations. So this keeps on going. So let's see like what this will give if I run this. So this is giving me 3.146. So in four number of iterations. So earlier we were seeing like some 7, 8, like 11, 20. So here it's in four number of iterations. I'm getting this. So like a very fast. Method. So if I let's say take 0.001, like, let's see what I'll get. Now you can see that in 7 iteration, I am getting this another solution, which is 0.138. So depending upon like the initial condition, you can get like various solutions. Which you so Newton-Raphson method like is giving me a like faster convergence rate. Let's say if I'll use this. What was that? The other function which we have on the practice assignment which is given. I'll replace this here and let's see. Let's say if my initial guess is true, uh, what I'm getting. So I'm getting some the other like some large solution, and it's like it's the Newton-Raphson method is like going on for all iterations, and the error is also like not very small. So the error is increasing, so it is not covered. So my initial guess is wrong. So not wrong, like it's not a very good initial guess. Let's say if I take this initial guess as 0.0001. Okay. Let's see if and it give me a number. So this is also not giving me a good convergence. Okay. Okay. Sorry. This I have not changed the DF. That's my bad. Okay. So we have to change the derivative. So F we have changed, but we have not changed the F dash of X. So if I do this, I'll just instead of doing this derivative, that's not ChatGPT to do. Don't have too much effort. Find the derivative of so this is my derivative. So I'll just replace it here. The very complex derivative. You can see. This you can do in MATLAB also. The derivatives can be seen. Whenever I think we see symbolic computations in MATLAB, we'll see how we can do. I don't think. I think we are going to see somewhere in some module how we can do symbolic calculus, like doing derivatives, all these things. So that's 0.87 into minus 25 by x square divided by 6 minus 25 by x. So this is my derivative. I think this is, yeah. Now we'll see how the solution will end up. Yeah. Now we can see that our solution is 0.1768 is the solution which we also got last time using the bisection method. So this was the solution. And let's say if I take this initial guess instead of this 0.8 and take initial guess 2, so this is not converging. So I have to use, let's say if I take one initial guess, this is not convergent. So basically I have to use uh, in this, where is that? Element wise multiplication, division we have to do, right? Right, not this. Uh, yeah, 0.1 also. Yeah. So this was our solution. Like if we are going, our initial guess is going beyond our solution, like then it is not giving convergence. If the initial guess is below our solution, like below 0.17 or something, then we are seeing convergence. So for this, so let's say if I take 0.2, just right side of our true solution, just to the right side. Let's say if I get some, yeah, I'm getting. Uh, let's say if I take 0.5, ah, it's very sensitive. So even if I take 0.3, it is converging. If I go to 0.4, it's not converging. So that's why, like, as I've said, like initial conditions are very important when I want to find out the solution of nonlinear equation. So here, it's like very sensitive thing. So I can choose whatever I want. Okay. But this was not converging. So trial and error, by trial and error, if I see like up to 0.3, it is converging. After that, it's not converging. So let's see what what was there in the practice assignment. In the practice assignment, this was the equation. So everything is good. Okay. 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 So okay, okay. Dash of x is also given. None. Okay. So they are telling to solve the first iteration using 0.3 as my initial guess. Then report the value of x1 of 10. So here I don't I don't want it to run for 50 iterations. Like I just want, okay, let's say we'll run and we'll see what we get. Okay. So I'll just remove this. I'm just removing this colon here so that I want to print it. I want to print this. I want to print the new guess and also I want to print the error. So And I'll also, what I'll do is I'll also print the I value. This is a very bad way of printing, but I'm just doing it to see. Like you have to use display or print or something else, like printf or something else. But yeah. So now you can see that at uh, uh, in the first iteration, xi is 0.0014, 0.1004, and the error is what is the error? 0.1996. Next, as we go to the second iteration, the error is 0.0344. And next, the after the third iteration, the error is reducing. And you can see, like, with the increasing number of iterations, our error is reducing. That's what we want, like, the error to be reduced. So the tolerance, like, is like basically they are saying that tolerance should be 10 to the power of minus. So I'll run this again. I'll see how many iterations does it take to for the tolerance to go below 10 to the power of minus. So here you can see like six iterations. After six iterations, it will be below the tolerance. This is six, yeah. So everything like you can see, like we have solved it, all the answers are correct. So this is the first problem in the practice set. So we need six iterations to converge, basically to go below the tolerance, error to go below the tolerance, and these are the errors, and this is the first iteration value, all this. If we solve this with the fixed point iteration, how will it go? So we'll see how we can solve this the same thing using the fixed point iteration. So basically, I have to code this function and replace this with this. So which is 1 by 10 minus 0.87 into log 6 plus 25 by x. We have so they have also given us the initial condition, initial guess. Sorry. So like no need to worry about initial guesses. Like in exam, you will always like whenever this kind of problem is being given to you, you will also get a initial guess. So like you don't have to get a random. You don't have to take a random initial guess. So you will be given. So uh, no need to worry about that. Okay. So we'll solve this with the fixed point iteration. Let's see how it goes. Yeah. Basically, after five iterations, it is converging. Okay, I just want my uh, values to be printed so that I can see at what iteration what is the value of guess and also the error. So Initial guess after the first iteration is 0.16, and after second iteration, it is asking me the initial guess, which is 0.1788. And after third iteration, 0.176. Let's see if my answers are correct. So whatever which I'm getting, the answers which I'm getting are correct. So this is how we can use fixed point iteration to solve this uh, equation. Let's say if you want to use the same things, uh, let's let's just we are we will use fsolve to do it. So we have not seen fsolve, right? So yeah, uh, let's we have we'll use f0 to solve this. So interesting thing, we have to use f0 to solve. So in f0 we have to take these initial guesses 0.3 and what is 0.5, and we'll see if it is solved. Some section, there is some error in the code. So f0 is not giving us uh, the result. So we are saying that report a value of 999 if f0 throws an error. Let's say if fsolve is giving me a solution. So fsolve has the same kind of syntax, but we need only one initial guess for fsolve. Uh, see. So instead of x naught, I'll just give my initial guess, which I have 0.3. If I use fsolve to solve this, let's see what I'll get. So I'm getting 0.1768. So fsolve is solving. Yeah, let's see. These two we have solved. Let's see if the answers are right. Yeah, this is fsolve is 0.1768. This is right. Yeah. So these two are correct. So like fsolve and f0, these are both kinds of commands uh, or the functions, inbuilt functions in MATLAB, which you can use to solve the nonlinear. So fsolve basically is a very good method which you can use, like a lot of uh, assignment 5, problem 4. Okay. Uh, So fsolve and f0 you can use. So for f0 you should have two initial guesses, and the two initial guesses uh, should have opposite f values, opposite negative, sorry, opposite signs of f values. So for fsolve you should like you need only mm, one initial guess, and it is a very efficient method, like kind of like you can say Newton Raphson, but it's not like Newton Raphson, but it's like a very evolved method, like better than Newton Raphson. So fsolve you can use directly in build party function. Like in other programming languages also you have this kind of fsolve. Like in Python also I think there is nonlinear uh, solve something kind of a function. So this what is there? Basically, the here f of t, whatever you take, is f x of t. So hint, what what kind of hint you want? So take this f of t as x of t. So replace this x of t with f of t and you solve it. So everything is given, xt is like vr is given, like you know the value of gr, ver is given, v0 is given, everything is given. So r is also given. So and so you have to solve this. F of t is equals to this equation. You have to solve this. So whatever you get is the solution. So what is the hint? So nothing. Like, simple problem only. So, uh, do you have any doubt in this? You got the hint? See, they are saying that you have to find f0 to find time when the ball reaches the ground. When does the ball reaches the ground? When x of t becomes 0. So the position should become 0. So that's what it is like. If the position becomes 0, it means like uh, the ball is reaching the ground. So that's why f of t is 0 is nothing but like x of t is equals to 0. So replace x of t with f of t and yeah, if we have seen f solve, then we have gone to this uh, we have gone to see this Newton Raphson in multiple variables. So we have seen the use of f solve. So you can have multiple variables and you need to find out the solution. So like this, like you can have system of nonlinear equations like this, which are functions of x, y, and also z, like three. So uh, uh, basically, we say states here. Like this is a Lorentz equation. So uh, if you are someone like from chemical engineering or mechanical background or like also biotech or kind of field, like you will relate this with this Lorentz equation. Uh, this comes a lot like when you study about nonlinear dynamics. So like here, like if you don't know, like then it's fine. Like, it's not a very good like it's not required that you should know the Lorentz system. So it's basically it gives chaos. So chaos is like a concept in which like a determinate systems a determinate system will have a very uh, typical behavior. So like if you change the initial condition a little bit and the states will vary a lot. So that's what chaos is. Like if you don't know, not a problem. Like, uh, just we have to solve uh, the equations here. So we are just going to see how can we solve. Okay, so the Lorentz system is given, and if I have to find out how can I solve using the Newton Raphson for this multivariate example. So here we have to find out the value of x and the value of y and the value of z. So our solution will have these three values. Earlier we have only univariate function and we had to find out the value of x. So this also like the derivation if you want, like you can go through the computational techniques course. in the same module 4, I think, like the derivation is given, like a simple thing. Like instead of f I by f dash of I, here we are like replacing this division of f dash of I with the Jacobian. So inverse of the Jacobian. Jacobian is nothing but like derivative of the functions, like a matrix of derivative of the functions with respect to all the variables. So first row will have dou f by dou x, dou f1 by dou y, dou f1 by dou z. The second row will have dou f2 by dou x, dou f3 by dou f2 by dou y, dou f2 by dou z, dou f2. Similarly, the third row will have differentials with respect to all the variables for the function 3. So you can take this as function 1, function 2, and this as the function 3, and you can get the initial guess. Like you take this initial, like you take this matrix, get the inverse of it, and you can get the initial. You have to take some initial guess, and then after that you will generate a new guess. And similarly, we go on check, keep on iterating till we get our solution. So here the Jacobian matrix, like the main thing is like when you have this system of nonlinear equations and if you have some Jacobian matrix, right? So this Jacobian matrix should be invertible. Like otherwise, you will uh, go into some kind of problem. Similarly, in Newton-Raphson also, here mm, f dash of xi should not become 0. Then it will go like to infinity. So we have to be careful that like this, uh, like otherwise, like you will get some divergence or you will not get the solution. So here also this should be invertible. So the Jacobian matrix should be invertible. Whenever I say it should be invertible, it means like the matrix should be singular. It means the determinant of J should not be equal to 0. Okay. So some like things which we have to remember. Okay. Like so the initial guesses should not make this Jacobian matrix to be similar. We'll see we'll see how like the same thing, like the Lorentz system. Where is it? Yeah. So this is my Lorentz system function. I can solve using this Newton-Raphson. I'll just go directly to Newton-Raphson. I have the Jacobian. Rename it. Yeah. So I'm getting from this function, I am evaluating the value of function and also I am evaluating the value of Jacobian. Okay. So I'll input some initial guess. From that, I'll get the value of function and also I'll get the value of Jacobian. And to solve this, so we are taking this initial guess first, which is 1, 1, 1, and 1. And this is the tolerance criteria, and this is the thing. So we are getting the F and J, and also we are uh, generating the initial guess. And then after that, we have the error criteria that we should not go beyond the uh, like if it goes beyond, like if this goes below the tolerance, like we'll stop and we'll say that is our solution. Okay. Let's say if I run this, I have CLC clear, yeah. So I'm getting this solution 2, 3, 2, 3, and 1. So this is the solution of our Lorentz system, which we are doing it. Let's similarly, if I have mm, these initial guesses -1, -1, so I'll get -43, -43. So like this, I can do. I can use the multivariate Newton Raphson to find out the multiple system like solution of multiple non-linear equations or system of non-linear equations. So let's see how it will how we can do it for the problem which we had in the side. This practice. So instead of the Lorentz system, here we have only two values. Let's say x and y. So what I'll do is I'll create another. I'll keep this as it is, and instead of the Lorentz, I will say non-lin system Newton Raphson. Non-lin system. So I have only two variables. So I'll replace it. The first equation is I have this 12 minus y minus 25 x into y by uh, what's that? K plus y. So k is 50. I'll just write 50 plus. And the second equation. We don't have the third, so I'll remove it. What was that? 4 minus 60 into y by 50 plus y. So they are asking me in this problem solve. uh, I'll also use the Newton. So what is it? So the Jacobian also I have to change. Just ask ChatGPT. Yeah, very lazy. Find the Jacobian. Find the Jacobian of this system. Non-linear equation. So I don't need to do it like if I know symbolic computations in MATLAB because we have not gone through it. I'm just not using it. So ChatGPT is like very efficient these days to these kind of calculations. So it will give me a very good. So yeah, so this is my Jacobian and just use it whatever I have got. 25y divided by 50 plus y and I have minus 1 minus 1250 x. This is also into x into y. This is 50 plus y square. And I have 0 and what's that? 0 and minus 3000 by 50 plus plus. Okay. So this is the nonlinear system which I have to solve. And okay, here my initial guesses are 2 and 2 given in the problem. And yeah, for updating the, I'll save this function with the nonlinear this and so I'll call this instead of Lorentz this and all. So everything is good. Now we'll see what this will give me. I run it and there is some error. Some error is there. Multiplication operator. This comment I had written. Okay. Now I'll evaluate. Yeah. So this is my approximate solution. After 4 iterations, it is converging and the error value is also, yeah, 4 iterations it is. I forgot something here. Is that? I forgot to add column. After 4 iterations, I'm getting this solution. Okay, let's see if I use Fsolve. Uh, I'll use Fsolve to solve this. Let's say this is X and whatever I have, non-lin sys. This is the function and my initial guess is 2 comma 2. 2 semicolon 2, right? And I'll use nonlinear system. So see if we are getting the same solution even if you are using the Fsolve. So I'll just type the solutions and see if my solution is matching. 3.574. So both the solutions are correct. So we have seen Newton-Raphson to solve multivariate um, system of nonlinear equations. So like we can use Fsolve also. We can use this uh, code which we have written for Newton-Raphson, like multivariate Newton-Raphson. So both the things are giving us a good um, agreeable result. So whatever you want, you can use. Like if you want like a detailed method in which you want to observe every step, then you can use multiple multivariate Newton-Raphson. Or if you want like a direct result, like you don't want to know what is going on each step, then you can use directly uh, the fsolve command, and you can get the solution. So either way, like I'll say, if you are like a beginner, uh, it's better to solve. Sorry, I'm busy. So the thing is, like, if you want to learn, like, it's better to always code each and every method. Like, you can also include the regular Fuzzy methods, you can all the other methods which are there, and you can see in each iteration how everything is going. You can plot the results and learn a lot by doing the codes. Like, if you are directly using FSOL or F0, it's fine. Like, if you want like direct result, it's fine. But if you want to learn, like, code everything and you can learn. So you can learn more. So you will get a sense of what these numerical methods are doing, and it will be a very learning, good, enriching experience for you. Okay. So I think today we can stop here. Thanks for joining. Anjali, you have any questions? Do you have any questions, Anjali? Uh, can you hear me? Do you have any questions in this? Okay. Yeah, thank you for joining, Anjali. Uh, hope you have a good night. See you in the next week, hopefully. Yeah. Okay. Take care. We stop. Class. Good.